Alright, in section 3.6 we are moving on from our polynomial functions and looking at rational functions. With our polynomial functions, the graphs would have smooth continuous curves, and we had a domain that included all real numbers. So in 3.5 our focus was on polynomial functions, our domain was all real numbers, we had smooth continuous curves, no gaps, no breaks. In 3.6 we're focusing on rational functions, and I call something a rational function when I have a variable in my denominator, and you can see some examples of rational functions here. And when you look at the graph for one of our rational functions, you see that it is not a continuous curve. In fact, we've got a break here. We have a vertical asymptote where x equals -1, and we have a horizontal asymptote, so we have two breaks on our graph. So rational functions are not continuous. A rational function is a function whose rule is the quotient of two polynomials. Quotient is the answer to a division problem. So examples of rational functions, we've got 2 over 1 plus x, 3x plus 2 over 2x plus 4, and then here we have a quadratic equation or a quadratic expression in the numerator and a cubic expression in the denominator. The important part of a rational function is that you have a variable in the denominator. So let's put that in. We have a variable in x in the denominator. And because of that, therefore, anytime I see that little triangle of dots, that means therefore, I expect there will be limits on my domain. It will not be all real numbers. My domain will not be all real numbers for a rational function. Now, let's take a look at this graph. Our graph is for the function f of x equals 2 over 1 plus x. This is my first example I gave here. And when I graph this, I end up with two places where I have values that are undefined. So x cannot be -1. That gives me a vertical asymptote. A vertical asymptote is like a brick wall. My function approaches that value, that x value, but it cannot ever equal that x value. So it turns my function. Like if you took two magnets that had the same polarity and tried to put them together, it would turn the magnets. Functions turn when they approach that vertical asymptote, that brick wall. And then this function also has a horizontal asymptote at the x-axis. This horizontal asymptote, or HA, this one has an equation of y equals 0 because it is the x-axis. So we've got both a vertical and a horizontal asymptote with a lot of our rational functions. You'll never have more than one horizontal asymptote. You could have more than one vertical asymptote. In fact, let's look at some examples here. The domain is restricted in a rational function to all the real numbers that do not cause the denominator to be 0. So I've got to watch to see what values would cause my denominator to be 0. My challenge here for 1 through 4 is to find the domain of each of the examples of the rational function. So I'm looking to see where is my function undefined. What would cause my denominator to be 0? Well, in this first, when I look at my denominator here, I've just got x in the denominator. So if x equals 0, my function is undefined. So my domain is going to be any value of x such that x is not equal to 0, and I use fancy braces to express that domain. Anything but 0 is fine. Right here where x is 0, I have a vertical asymptote, x equals 0. That value is undefined, it's excluded from my domain. For this one, I have x squared in my denominator. Well, if I set x squared equal to 0, I would have to take the square root of both sides to solve, consider plus or minus, but 0 isn't positive or negative, it's just neutral. So I still end up with x equals 0 needing to be kicked out of my domain. So x can't be 0 here, it's going to cause my function to be undefined. So once again, I'm going to say my domain is all values of x such that x is not equal to 0. There's my domain. And I can see this vertical asymptote right there again at x equals 0. Notice a vertical asymptote is a line. I write it as an equation of a line. Now these two functions are not the same. Their graphs are not the same. When I have 1 over x, I have this pivot around the origin. One end is up, one side is up, one side is down. When I have 1 over x squared, that squared term in the denominator, these two end up mirroring each other and reflecting across that y-axis. Let me hit the autofocus. Make sure we are showing up as clearly as we can. All right, next we've got y equals x squared minus 1 over x, and as I'm looking at my function, I see that I've got some interesting stuff going on, but still I have just x in my denominator. So x being 0 is the only value I need to exclude from my domain again. X cannot be 0. I leave 0 out of my domain. Here's my vertical asymptote. X cannot be 0. And then this last one, x over x squared minus 1. Now I've got some more interesting stuff going on in my denominator here. If I take this denominator and I set it equal to 0 to see what would make that happen, because that's going to give me my values I need to exclude. I see that to solve this, I'm either going to have to take the square root of both sides, move that 1 over, take the square root, or I could factor this. This is difference of squares. It factors out to give me conjugate pairs. If I set each of those equal to 0, I get x would be -1 or +1, and those are the values I need to exclude from my domain. So my domain here excludes two values, all values of x from my domain, such that x is not equal to either -1 or +1. There's my domain for this one, and you can see that I have two vertical asymptotes. I have a vertical asymptote at x equals -1 and at x equals +1. Two equations for vertical asymptotes. Okay, now we're going to come back and we're going to talk about horizontal and slant asymptotes in a bit. So let's go ahead and let's finish this. A rational function will have values at which the graph is undefined. That's just part of being a rational function. These values show up as either holes in the graph. None of these graphs had holes. Holes in the graph if the function is not in lowest terms, or as vertical asymptotes. Those are my brick walls, and that's what we were looking at, vertical asymptotes, and that's what we see in these equations, because each of these functions are in lowest terms. I can't simplify any of those functions. Definition of an asymptote: a value the function approaches but never gets to. The distance between the function and that vertical asymptote, that distance gets infinitely smaller. And I just misspelled infinite. I stuck my E in the wrong space. Let's fix that. It's going to bug me. Infinitely smaller. So my graph gets closer and closer and closer. So right here, for example, it looks like these two curves start going straight up, but they don't. They keep moving closer and closer and closer to that asymptote. It's just that we can't tell the difference because that distance between the graph and the asymptote gets smaller and smaller. Both holes and vertical asymptotes are determined by the domain, which comes from the denominator of the function. There can be more than one hole or more than one vertical asymptote. A hole occurs for any value from the denominator that will factor out, any value from the denominator that factors out because the function was not given to you in lowest terms. So a hole is going to be something that factors out. We haven't had that example yet. Vertical asymptotes occur for any values from the denominator that remain when my function is in lowest terms. Each vertical asymptote is like a brick wall. It's never going to be crossed. Now it encourages us to go back and find the vertical asymptotes and holes of these examples. We already did that. we found the domain, and we showed that, you know what, each one of those values we exclude from the domain represents a vertical asymptote. Let's do some practice with these and see what we've got. We're going to first identify the domain of each rational function, and then we're going to classify the values that we exclude as either vertical asymptotes or holes in the graph. So we want to finish factoring anything that can be factored, and we need to identify the domain. That's first. First, identify the domain, then decide if those values we kicked out of the domain are vertical asymptotes or holes in the graph. So let's factor, find the domain, D for domain, and then we will evaluate those values. Let's factor this denominator. X squared minus 1 is difference of squares. That factors out to give me conjugate pairs. Conjugate pairs look exactly the same except the signs are different. Square root of x squared is x, square root of 1 is 1. Ah, look at that. So, before I get carried away, I've got it factored. I'm going to identify the domain. What in my denominator would cause my denominator to be 0? Well, a negative 1 here, a positive 1 there. So my domain is going to include every x value such that x is not equal to negative 1 or positive 1. I'm kicking both of those values out of my domain. But this function is not in lowest terms. To get this function into lowest terms, I'm going to cancel out any common factors. So in lowest terms, my function becomes 1 over x minus 1. That's lowest terms. So when I look at these two x values, one of them factors out. The one that factors out gives me a hole in the graph. This term factors out x plus 1. If I took that x plus 1 and I set it equal to 0, I get x is equal to negative 1. That's my hole in the graph because that's the one that factored out. The one that stayed put gives me a vertical asymptote. If negative 1 was my hole, then that means positive 1, x equals 1, is going to be the equation of my vertical asymptote. So I have a hole at the x value negative 1, and I have a vertical asymptote where x is equal to positive 1. Alright, let's do another. Remember, the very first step is to factor. I'm throwing pins over here, guys. Hold on. Okay, the very first step is to factor. So in my numerator, I can factor out a common factor x. I have x times x minus 3 in my numerator. My denominator, I can first factor out an x. That's going to leave me with x squared plus x minus 2. And then this is quadratic, so let's see if we can factor that again. So my numerator is x times x minus 3. My denominator is x times, and then I want to factor that quadratic. Looks like my signs are going to be different, 1 plus, 1 minus, because that's negative. 2 is prime. I want the 2 to be positive. Positive 2, negative 1 gives me that positive x in the middle. So here it is completely factored. My domain needs to exclude everything from the denominator that would give me a 0. So x value such that x is not equal to, well, I've got 0, negative 2, positive 1. If I put those in order from least to greatest, it looks like this. Those are my 3 values I need to exclude from my domain. And then I need to evaluate that. Let's go in and let's say, okay, do I have holes or vertical asymptotes? I've got 3 values to evaluate. Well, when I look at my function, x over x, anything over itself is just 1. So that is not in lowest terms. That's going to factor out. So x equals 0, I have a hole at x equals 0. But the rest of this remains when my function is in lowest terms. So these other 2 values that I excluded from my domain both represent vertical asymptotes. So I write them as equations. X equals negative 2, x equals 1. I have a hole at x equals 0. I have vertical asymptotes at x equals -2 and x equals positive 2. X equals -2, x equals 1, because I have those two factors. Sorry, guys. All right. I encourage you to pause the video, see what you can do with these on your own before you come back and look to see what I did. Follow your steps. Factor first. That's going to factor to x minus 5 and x plus 1 in order to get that -4 in the middle. I have two values in my denominator that give me zeros, places where the function is undefined, zeros for my denominator. So my domain is going to be all values x such that x is not equal to what would cause my denominator to be 0. So a positive 5, a -1. Remember, we're thinking about setting those expressions equal to 0 and solving to see what that would give us. So it changes that sign. These two values are excluded from my domain because they come from the denominator, factors in my denominator. Is my function in lowest terms? Well, it's not. I have factors in common in the numerator and denominator, so to get it in lowest terms, I would have to cancel that out. The thing that factors out gives me a hole in the graph. So I'm going to have a hole at x value -1, that's what factors out, and I'm going to have a vertical asymptote, the line x equals 5. Final example, factor numerator and denominator. Notice that I take my time to factor that common factor out of my denominator before I try to factor that quadratic. If I can't do it all at one go, you can't either. So don't try to get ahead of yourself and skip steps. Alright, I factored out my x, and then I'm going to factor this quadratic. Looks like that is a 1. It's going to have the same sign. Those signs are going to be negative. So -1, -1. X minus 1, that gives me a positive 1 at the end. Negative x is -2x in the middle. Perfect. So I did my factoring. Now I need to define my domain. My domain is going to be all x values such that x is not equal to, and I have two unique values in my denominator. I have three factors listed here, but two unique values in my denominator. I've got x equals 0 and positive 1. Those are the two values I exclude from my domain. Now the last step is going to be to simplify. One of those factors cancels out. So my function in lowest terms is x plus 4 over x times x minus 1. I still have both of these values represented in my denominator. So even though my function was not in lowest terms, I don't have a hole in the graph. I have a vertical asymptote at both x equals 0 and x equals 1. Alright. So, transformation review. This takes us back to see what we knew, what we remember about how to graph with transformations. We're going to use our knowledge of transformations and the examples that we did on the first page to sketch a graph of our rational function. Okay, first thing we're going to do, identify the given transformation. Well, I've got this negative out front. That negative out front is going to reflect across the x-axis. From our pattern of transformations, we know that that's what that negative out front does. So I've got 1 over x squared, and then I need to reflect it across the x-axis. Well, right here is my graph for 1 over x squared. Both ends are up. So that means if I just reflect that across the x-axis, it's going to look like this, where both ends are going down. And I have a vertical asymptote here and a vertical asymptote or horizontal asymptote there, because that was what was in the original, the parent. Y-intercept, well, there is none, because that y-axis is a vertical asymptote. Zeros, roots, values that I have x-intercepts. Again, there are none because a horizontal asymptote is my x-axis. Domain, what values am I excluding from the domain? Well, I've got this vertical asymptote here at x equals 0, so that is going to exclude 0 from my domain. So I'm going to say my domain is all values x such that x is not equal to 0. My range goes from negative infinity up to 0 but not including 0. So from negative infinity up to but not including 0. I've got a horizontal asymptote here at y equals 0. And my end behavior, what is happening as x gets large? So let's look at that. As x approaches positive infinity, what is y doing? Where is y going? As x moves off toward positive infinity, this y value is getting closer and closer to that horizontal asymptote. It's getting closer to 0. As x approaches negative infinity, I'm moving out this way. What's y doing? Well, again, that y value is getting closer and closer to my horizontal asymptote. Y is approaching 0. All right, one more. 1 over x plus 2, and then I've got a minus 3 out here. So let's look and see what we can use pattern of transformations from our first page. Which one of these equations we can use? Well, it's not squared, so let's do this one. 1 over x. If I use 1 over x as my parent function, I've got one side up, one side down. Left side's low, right side's high. What transformations am I doing here? Well, anything attached to the x is horizontal. So this is going to do horizontal shift. X plus 2 would be to the left 2 units, and then this minus 3 tacked on at the end is going to be down 3 units. So I'm going to take my horizontal and vertical asymptotes at 0 and 0. I'm going to shift this vertical asymptote to the left 2 units, so right there at negative 2. And then down 3 units, so instead of at 0, we've got y equals negative 3. And our function is going to be right here somewhere, right? Left side's down, right side's up. Let's check out some values. We kind of guessed, I just sketched it, so we kind of guessed at our intercepts. We are crossing the x and y axis here. My domain value I'm leaving out now is negative 2. So my domain is all values of x such that x is not equal to negative 2 instead of 0. My range includes every value except for negative 3. So range is all values of y. Let's go ahead and do it this way. Negative infinity to negative 3 or negative 3 to infinity, not inclusive. My vertical asymptote was that x equals negative 2. My horizontal asymptote, y equals negative 3. We need our intercepts and our end behavior. End behavior let's do first because we did it once over here. As x gets large in a positive direction and as x gets large in a negative direction, what is y doing? Well, as x moves to positive infinity, y is getting closer and closer and closer to that horizontal asymptote, negative 3. As x moves to negative infinity, y is also approaching that horizontal asymptote, negative 3. So this end behavior, hopefully you can see that my horizontal asymptote controls my end behavior. That horizontal asymptote is about where I'm approaching what y value is being approached as I get large with my x value, as I approach the end. Alright, y-intercept where x is 0. If I plug in 0 here, I have 1/2 minus 3. If I plug in 0 for x, I would have 1/2 minus 3. And 1/2 minus 3, well, if I have 1/2 minus 3 is going to be negative. It's going to be a negative 2.5. So if x is 0, y is a negative 2.5 or a negative 5/2. 2.5, I didn't sketch it very well. I should have come on down to about right there. 2.5. The x-intercept happens where I set the function equal to 0. We are not going to take the time to work that out right now. I promise I'm not going to give you that question at this stage in the game. I would set this equation equal to 0 and then solve, just because the video is going to go quickly. I want us to not focus on that bit right now. See if you can do that. See if you can set that equal to 0 and come up with negative 5/3. Okay, third page. How do we find those horizontal or slant asymptotes? Oblique and slant mean the same thing. My example of an oblique or slant asymptote is this function right here. That's an oblique or a slant asymptote. How do I find those asymptotes? Well, these asymptotes apply primarily to the end behavior of the function. They're not like that brick wall vertical asymptote, so sometimes they could be crossed. I can have more than one vertical asymptote, but there will not be more than one horizontal or slant asymptote. My vertical asymptotes are determined by the denominator. Horizontal or slant asymptotes are determined by the degree of the numerator compared to the degree of the denominator. Now, when I compare two different degrees to each other, they can only compare in three different ways. One can be less than, one can be greater than, or they're going to be equal to each other. So the first case, if the degree of the numerator is less than the degree of the denominator, we have a horizontal asymptote at the x-axis, and that equation for the x-axis is y equals 0. Well, what does this look like? An example of this would be f of x equals 1 over x. Here, my degree of my numerator is 0, and the degree of the denominator is 1. So my degree of my numerator is less than the degree of the denominator. Another example, let's do g of x is x squared over x cubed. Degree of numerator is 2. Degree of denominator is 3. So the degree of the numerator is less than the degree of the denominator. My horizontal asymptote is going to be at the x-axis, y equals 0. So for both of these, horizontal asymptote is at y equals 0. The next way things can be is if the degree of the numerator is equal to the degree of the denominator. When that happens, I have a horizontal asymptote at the ratio of the leading coefficients. What does that look like? Well, f of x equals 3x plus 5 over 2x minus 7. Both of those degrees are just 1. I have x in the numerator, x in the denominator. So I look at the ratio of the leading coefficients. My leading coefficients are 3 and 2. I will have a horizontal asymptote at y equals 3/2 for this one. Let's do another example. G of x, let's say x cubed minus x squared plus 7 is my numerator. 2x cubed plus 5 is my denominator. Both numerator and denominator are third degree, so those degrees are equal to each other, which means I will have a horizontal asymptote at the ratio of those leading coefficients. Well, my numerator, that coefficient is 1. 1 over 2, so I have a horizontal asymptote at 1/2. And finally, when the degree of the numerator is greater than the degree of the denominator, I don't have a horizontal asymptote, I have a slant asymptote or an oblique asymptote. This only happens if the numerator is greater, if it is greater by 1 degree. If it were greater by 2 degrees, I'd have a parabolic asymptote, and then it just gets more interesting than that by now. We're just going to stick with slant asymptotes, and you're not actually going to have to find the slant asymptotes. You just need to recognize when that happens. So let's do an example of this. F of x equals 3x squared plus 5 over 2x minus 7. My numerator is degree 2, my denominator is degree 1, so I know I'm going to have a slant asymptote. And again, you're not going to be asked to find this equation. you are in college algebra, rather than business college algebra, that's something that you have to do, but that's not something that we do in this course. All right, note, find the horizontal and slant asymptote of each of the examples from the first page. So let's go back and look at this first page, and let's look at these horizontal or slant asymptotes. Well, right here I have a horizontal asymptote at y equals 0. And I know that that's going to happen because degree of the numerator is 0, degree of denominator is 1, so this degree is less than the denominator. Once again, degree of the numerator is less than the degree of the denominator, so I have a horizontal asymptote at y equals 0. Here I have a slant asymptote. If I compare the degrees, for numerator is second degree, denominator is first degree, so the degree of numerator is 1 greater than the degree of the denominator. So I have a slant asymptote. This slant asymptote is actually at y equals x. It's my parent function, linear function. And then here I have, again, the degree of the numerator is 1, degree of the denominator is 2. I have a horizontal asymptote at the x-axis. I don't have an example on this page of a horizontal asymptote that is not at the x-axis, but there is one here. Right there I have a horizontal asymptote at -3. And that we found by using those transformations of functions. That was a different look to our equation. Okay. Practice finding those horizontal and slant asymptotes for these functions. So let's compare the degree of the numerator to the degree of the denominator. Here, those degrees are the same. So we look at our ratio of our leading coefficients. I'm going to have a horizontal asymptote at y equals 2 over 1, which is just 2, because the degrees are the same. Right here, my degree of my numerator is 1. Degree is 1, denominator is degree 2. The degree of the numerator is less than the degree of the denominator. When that happens, I have a horizontal asymptote at the x-axis. So the degree of the numerator is less than the degree of the denominator. Here, what do you think? Degree 3, they're the same again. So when those degrees are equal, it's the ratio of the leading coefficients. My leading coefficients are 6 and 6, so I have a horizontal asymptote at y equals 1. All right, excellent, excellent. Let's look at our last page. Graphing rational functions. Now this is something that you're going to have to get lots of practice in to get comfortable doing before our exam. But this is it's a good set of steps right here. First, you find the domain of the function. That's always what you do first. Always, always. Identify the domain. Then I factor and cancel if I need to. Remember that if something cancels out, it causes a hole, not a vertical asymptote. Find the horizontal asymptote by comparing the degree of the numerator compared to the degree of the denominator. Then set your denominator equal to 0 to find any vertical asymptotes. Find the y-intercept if x equals 0 is in the domain, as long as that's not excluded from the domain. Find the x-intercepts if y equals 0 is not a vertical. That's wrong. I need to fix that. That needs to be a horizontal asymptote. Make that correction, guys. Y equals 0 if it is not a horizontal asymptote. Pick x values in the intervals between and outside the asymptotes to plug in and find anything that you still need to clarify. Okay, so we got two functions that we're going to graph. First of all, we've got 3x over x minus 1. Nothing can be factored, so I think about, okay, what's in my domain? Well, my domain is limited by anything that causes my denominator to be 0. If I set this equal to 0, I would get 1. Cause me to have 0 in my denominator. So my domain is every x value except x equals 1. That's excluded from my domain. My functions in lowest terms. So I'm not going to have any holes in the graph. I will have a vertical asymptote for this value I excluded. So x equals 1 is a vertical asymptote. Let's go ahead and put that on our graph. There's our vertical asymptote at x equals 1. What about a horizontal asymptote? Let's compare our degree of the numerator to the degree of the denominator. Well, degree of the numerator is x to the first, denominator is x to the first, so they're the same. When our degrees are the same, we have a horizontal asymptote at the ratio of the leading coefficients. So I have y equals, well, 3 over 1 is just 3. So y is 3 is my horizontal asymptote. There's my horizontal asymptote there, vertical asymptote there. Can I find a y-intercept? Well, x equals 0 is part of my domain, so we're good. So if I plug in 0 for x, I get 0 over negative 1. 0 over anything is just 0. So my y-intercept is 0, 0. And you know what? 0 here, 0 there. That origin is both my y-intercept and an x-intercept. Now I can start graphing my function at this point because these two asymptotes are going to turn my graph. It goes through this point, so when I go up, it's going to curve back and get closer and closer to that horizontal asymptote. When I move down from this point, it's going to go closer and closer and closer to this vertical asymptote. And I've got the left half of my graph done. All I need to do is figure out the right half of my graph. Well, the right half of my graph is either going to be down here or it's going to be up here. I just need one point to figure that out. How do I choose a point? Well, I pick a point that is on the side of the vertical asymptote that I need to check. My vertical asymptote is at 1. I need to check this right side, so let's check 2. Let's try x equals 2 as our additional point. If I take x equal 2, I get y equals 3 times 2 over 2 minus 1, which is 6 over 1, or just 6. So where x is 2, I have the point y is 6. 1, 2, 3, 4, 5, right there. And then I can do the same thing. If I go up from this point, it's going to get closer and closer to that vertical asymptote. If I go down, it's going to be curved by this horizontal asymptote. And there's the graph of this rational function. So once you get your asymptotes in place, things should start falling together pretty quickly. All right, one last example here. Domain comes from the denominator. We've just got an x, so that can't be 0. X such that x is not equal to 0. Is my function in lowest terms? Well, yes. Nothing's going to simplify and cancel, so there are no holes. I have a vertical asymptote at this value I excluded from the domain. So right here on my y-axis, I have a vertical asymptote. X equals 0, not y equals 0. There we go. Horizontal asymptote. Compare the degree of the numerator to the degree of the denominator. For horizontal asymptotes, they have the same degree. So I use the ratio of the leading coefficients, 1x over 1x. So my horizontal is at y equals 1. So sketch that into your graph. That's going to shape your graph. Alright, I know I have two sides. I have this vertical asymptote brick wall. I have one side of the graph is going to be over here, up or down. The other side is going to be over there, up or down. Y-intercept. Can x equal to 0? Well, I go up here and I say nope. X equals 0 is excluded from my domain, so there is no y-intercept. That's because x equals 0 is excluded from domain. What about x-intercepts? Well, that happens when y equals 0. So let's do that. Let's set y equal to 0. Always, always, my next step is going to be multiply both sides by the denominator to clear out that denominator. Anything times 0 is 0. So I'm left with 0 equals x minus 2. You're always going to get there. 0 is equal to your numerator. So I solve for x here, and I get where y is 0, x is 2. So 2, 0 is my x-intercept. 2, 0 is right here, and that lets me start sketching my graph. So it's contained by those asymptotes as I move away from the point that I know. And I'm done with the right half of my graph. The right half of the graph exists down here. Now I need to figure out the left half. Now, because I don't have an x squared here, I don't expect this left side to be down. I expect it to be up above the horizontal asymptote. How can I check to be sure? Well, I'm going to pick an additional point that is on the correct side of my vertical asymptote. My vertical asymptote is at 0. I need to check this side, so I'm going to use x equals -1 as my additional point. If x is -1, I have -1 minus 2 over -1. -1 minus 2 is a -3, and -3 divided by -1 is a +3. So where x is -1, y is 3, and that was what I was expecting. So I use the asymptotes to curve my graph, and we're done. Good job.